Hello everyone. Today's topic is the dense convolutional network or the DenseNet. The DenseNet is a variant of the convolutional neural network and is typically used for image classification. A DenseNet is made up of multiple dense blocks and transition blocks. The key concept in a DenseNet is the dense connectivity pattern. This pattern means that each layer in the network is connected to every other layer. That is, all the layers are connected to each other. Each layer receives its input from all the previous layers, and each layer passes its output to all the subsequent layers, to all the next layers. If there are n layers in the network, that means there are L into L plus 1 by 2 connections. For example, if there are 11 layers, then there are 66 connections. Two key benefits of this pattern are better flow of information across the network and fewer number of parameters, less parameters. Less parameters mean a smaller network that takes less resources, that takes less GPU, less CPU, less computation power. Let us look at a dense block with 4 layers. Let the first layer be L1, the second layer be L2, the third layer be L3, and the fourth layer be L4. Here x0 is the input image, x1 is the output of layer 1, x2 is the output of layer 2, x3 is the output of layer 3, and x4 is the output of layer 4. The input to layer 1, L1, is the input image. The input to layer 2, that is L2, is the concatenation of x1 and this input image. We can write the concatenation as x0, x1. This is the input image, x0, and x1 is the output of the previous layer, which is L1. Similarly, the layer L3 has the output, the concatenation of x0, x1, and x2. It is receiving x1 from here, and it is receiving the input from here. Finally, the input of layer 4, that is this layer, is the concatenation of this input image, the output of layer 1, that is x1, the output of layer 2, that is x2, and the output of layer 3, that is x3. Now let us look at the output of each layer. Let h1 be the transformation function that is applied by layer 1. Let h2 be the transformation function applied by layer 2. Let h3 be the transformation function applied by layer 3, and let h4 be the transformation function applied by layer 4. The inputs to layer 1 are the input image. The input to layer 2 is this concatenation. The input to layer 3 is this concatenation, and the input to layer 4 is this concatenation. Still here. Now if we focus, the output of layer 1 is x1, so this equals x1. The output of layer 2 is x2, so this equals x2. The output of layer 3 is x3, this is the equality, and that equals x3. And the output of L4 is x4, so this equals x4. So this was a basic dense block with 4 layers. We call each layer in the dense block a dense layer. The dense layer is not a single layer, rather it is a composite function or a composite layer that consists of 3 layers. The first one is the batch normalization layer. Its purpose is to standardize the input. It standardizes the input so that it has a mean of 0 and a variance of 1. Secondly, the rectified linear unit layer. It drops all the negative values in the input and converts them to 0. For example, if the input is -1, 2, 3, -3, 0, a ReLU applied on this or a rectified linear unit applied on this will simply convert the negative to 0 and the positive remain as it is. Mathematically, ReLU can be written as finally, we have the convolutional layer, which is a typical convolutional layer that we have studied before. The transition block occurs between dense blocks. Its purpose is to facilitate the flow of information from one dense block to the next dense block. It consists of 3 layers. The first one is the batch normalization layer. This layer normalizes or standardizes the input so it has an average of 0 and a variance of 1. The second is a convolutional layer. The filter size is set to 1 by 1 and there are n units or n filters in the layer. The number n is chosen carefully according to the problem. The final is the 2 by 2 average pooling layer. The transition block summarizes the information or downsamples the feature maps that are coming from the previous dense block. For example, there are 32 units here and the dimensions of an input are 128, 64 and 64. As this input passes here from the batch normalization layer, the dimensions remain the same. But this layer, it will change the dimensions to 32, 64 and 64. The number of feature maps or the number of channels are reduced to 1/4, that is to 32. Finally, the average pooling will decrease or reduce the width and the height of the feature maps by half. So the resulting dimensions are this, downsampled. This is a complete DenseNet architecture. There are 4 dense blocks, dense block 1, 2, 3 and 4. And there are 3 transition blocks 1, 2 and 3. First of all, the input image is passed to a convolutional layer which is followed by a polling layer which is followed by the first dense block. The dense blocks are where the dense connectivity pattern occurs. That is, each layer is connected to every other layer in a dense block. So these are the layers in this dense block. This one is connected to this one and this one is connected to this one and this one is connected to this one. Dense connectivity. The first dense block is followed by a transition block which is followed by another dense block. Again there is dense connectivity in it, followed by a transition block, then a dense block again with dense connectivity, then a transition block, then another dense block with dense connectivity. Finally, there is a global average pooling. The global average pooling layer aggregates the features from the dense block and passes them to a fully connected layer. This layer has up to 1000 units and this number corresponds or equals the number of categories, the number of classes in our image data set. And finally, there is this output. Just by altering, by changing the configuration of this architecture of the dense block, the number of layers in the dense block, the number of filters in those layers, we can come up with 4 state-of-the-art DenseNet architectures, which are DenseNet 1-to-1, DenseNet 1-to-1, DenseNet 169, DenseNet 201 and DenseNet 264.